right, so today we're really going to do finite elements, okay? So we're going to start with a model, our model problem. All right, so this is going to be for a domain where x goes from A to B. Subject, this time, to Neumann boundary conditions on both ends. So all right, we're going to develop the weak form. So three-step process, right? First is to move everything to one side of the equation. That's already done. We're going to multiply by a test function. We're going to integrate over the body. Then we're going to integrate by parts to shift some of the integration onto the test function. Then we're going to apply the boundary conditions. Okay? And so we've done that a few times now. So I'm just going to write it down, what the result is. So the body goes from A to B. Okay? If we define the bilinear operator, and the things involving only del U, right? And we're going to solve this equation. So even though they're equivalent, what we did before was we inferred a quadratic functional from this thing, and then we used the standard Ritz method. Okay. Now we're just going to solve this directly using a Galerkin approximation. Okay. And so we talked about that before. The Galerkin approximation is where your test functions or your arbitrary things use the same interpolant as your approximation to U. We talked about that in the weighted residual form. It's just the only extra step between here and the standard weighted residual form is that we've used the integration by parts scheme. Okay, so U is going to be approximately equal to UH, which is equal to okay, so the UJ are approximating functions of degree n minus 1 because you have a constant term, right? And the uj are unknowns. They're what we're going to solve for.